Okay, so what we're going to talk about right now is the relationship between time domain and frequency domain. They're extremely closely related, but they are also completely different. And you'll see what I mean in a second. Well, you'll see what I mean when I advance my slides. Okay, so first we should talk about different types of waves. I know we just talked all about waves, but here are three different types. So we've got a periodic wave, which I talked about a lot in the last set of slides. Those are waves that repeat themselves, periodic, right? So it's going to happen periodically, right? It'll start over periodically, essentially, is what it's saying. A pure tone is a periodic wave, and that's a one sine wave, like only one sine wave, not two or three overlaid on top of each other, would be a pure tone. Although you can have more than one sine wave laid on top of each other. That would just be a complex tone. So it wouldn't necessarily look like your perfect sine wave if you have multiples overlaid, but it would still be periodic. You could look at it and see where it begins to repeat itself. So those are periodic waves. We've also got aperiodic, which are waves that do not repeat themselves. You can think of this like noise, basically. If you look at a signal of noise, which I don't have one here, but I'll post one so you can take a look at it. It doesn't repeat itself at all. It's just kind of scratchy. And then also clicks like that, clicks or bursts, tone bursts, noise bursts, things like that. They don't repeat themselves either, and they'll show up just as kind of like big dark splotches in a spectrum, or if you're looking at a waveform, they'll just kind of be like a sharp spike in the waveform. And then mixed, you can have both. You can have a combination of periodic and aperiodic sounds. So you can have like a noisy pure tone. You can have, say, music played on a guitar that has some distortion overlaid. So you still have the melodic portion of the guitar, but then you've also got this kind of crunchy distortion on top of it that is not periodic. So these are your three basic types: periodic, aperiodic, and mixed. We're going to assume, just like when you took physics, everything is frictionless, right? They just make these assumptions that everything is frictionless. All the things that we don't want to talk about don't exist. So for the beginning portion of this class, we're going to kind of look at periodic waves with the assumption that noise isn't a thing that's going to be there. Of course, noise is definitely a thing that's going to be in any signal that you record, but it's easier to talk about different signals with a completely periodic, clean, I was going to say tone. It doesn't necessarily have to be a tone, but a signal, clean signal. So that's kind of where we're going to start, is with these clean signals. And we'll talk about noise as we get deeper into the class. So let's talk about pure tones. They're represented by sine waves. And in fact, I refer to pure tones as sine waves. Most people do, because their representation in a waveform looks like a sine wave, first of all, which is interesting. And then also mathematically, they can be a sine wave too. So their waveform looks like their actual mathematical form. So their real form coming through a microphone looks like their mathematical form, which is kind of interesting. So what does it depict? So what you're seeing here, I should show this to you. This is a circle, and all of the sine wave is basically derived from a circle. Where is the wave at any point on the circle? And the P is representing pressure at that moment. So you can see that the 0 point is this that's kind of floating right through here. So right here is where the sine wave actually begins. It's crossing over the 0, and that's one full period right there. So you can see how this moves around the circle, and as the graph paper kind of gets pulled on beyond it, it's tracing out this sine wave. So what we've got, if we think about pressure, I'm going to wait till it comes around again. So here is high pressure coming, let's say, out of the vocal folds. So what you've got first is the vocal folds are vibrating out. They're gonna move out and open and allow air to come out. Then they're going to shut again. And so, as you know from the previous section, we've got this high air pressure system that's moving up out of the larynx at this point. If you're talking about a guitar string, you pluck the guitar string and it pushes the air in front of it. An electric guitar really actually does this based on electronics, but like let's say an acoustic guitar, so you hit this and the string is going to push the air molecules ahead of it. So you start with high pressure, so you'd start right here, so then pressure is going up and then pressure is going down, just like we saw before. And so what it does is it traces out this perfect sine wave. And this, again, depicts displacement over time, right? So this could be displacement of air, but when it reaches your eardrum, this could be displacement of the eardrum, right? So displacement of the membrane, displacement of the membrane, and so it'll actually push on it, on the membrane. The sound waves will push on the membrane, which is, exactly what you would think, the tympanic membrane. There it goes, finally clicking. You can also think about this as a microphone, the displacement of the small diaphragm that's in the microphone. So that's going to go supposedly the opposite way of the way that's coming out, right? So high pressure this way is going to be the opposite when it reaches my microphone or my ear. So high pressure is going to push the microphone down, so the displacement will actually be in the opposite direction, but it's still essentially the same thing. So we could be showing voltage, we could be showing displacement of the tympanic membrane, we could be showing pressure changes in the air. It's all sine waves. So we've got a couple different characteristics of this though, right? So number one, of a periodic wave of simple harmonic motion, the first one is that it's going to repeat, and you can see this happening here. It's repeating over and over. This is true for the guitar string, this is true for our vocal folds if we're not changing the frequency, right? So if we're just holding the same note, it's periodic. The pattern of vibration is going to repeat. It's not going to change, which is the second point here. All of the cycles take the same amount of time to complete. And in fact, that cycle time is frequency, right? So it's how many cycles per unit of time is frequency. Usually we use second. How many cycles per second? Hertz is measured in seconds, cycles per second. So it's how many times do you actually cycle through in 1 second, and that's your frequency. Tuning forks and pendulums both move in simple harmonic motion, and I have my tuning fork right here. Not sure if you can actually see this thing moving because I don't have a strobe light yet, although man, I should really order one. That would be cool. So, okay. You should be able to hear this. So that's very much like an actual sine wave. If you were to replicate one on your computer in Audacity or Prot, it would sound a lot like what's going on right here. Now, and if you've taken any of the other classes with me, when you talk about bone conduction, you know that another thing that I can do with this microphone is I can use bone conduction, sort of. And so now we're not letting this wave travel through the air. The wave is actually traveling through the tuning fork into the body of the microphone, but it still sounds the same. It's still a sine wave. Okay, next. So this is probably like half of you just died right now, I'm guessing, but it's okay. Come back to life. You're fine. You don't really need to, I'm not gonna make you like compute this from scratch. You do not need to compute this from scratch. What I want you to know is, what the heck does this actually mean? So xt, and if you remember in math class, we'd have like f of x, right? So it's a function of x. You write that instead of y. So this is x of t. It's okay. It just means we're finding a number. Don't worry. Totally cool. We're finding a value for t. And t in this case is just time. So if you look at this picture down here, time is going from 0 right here. Oh, what? Okay, time is going from 0 right here this way. And so what this equation is doing is it's going to find where the wave is at any moment in time. That's all this equation is doing. Okay, so there's some parts here that we should talk about. So A, the amplitude. The equation is A, amplitude, times sine. And the sine is of 2 pi ft plus phi, which is a Greek letter. So there's a lot of crazy stuff in here, right? But you might notice a couple things. One is 2 pi. You know, that sounds like the area of a circle, 2 pi r. And that's true, because if you think back to this slide, we're kind of tracing out a circle. So that's where that comes from. And then let's talk about the other things. Sine, of course, is a mathematical term. It's a formula that we can use. A is your peak amplitude. And so if you look at A, it's all color-coded for you, right? So hopefully nobody's colorblind in this class. Although if you are, I do research with color vision, and you should certainly email me. Let me know if you're colorblind. We should talk. Anyway. And then also I'll change the colors on the slide for you. So A is peak amplitude. And then you can see on the picture right here, this is just what amplitude is. It's how tall the wave can get from the center line. F is frequency. Well, we talked about frequency, right? It's just how many cycles per second. So it's going to be the measurement from the peak of this wave to the peak of this wave over time. So how many of those can fit into 1 second? That's your frequency. And then red is for phi, and phi is your starting phase, and that's here in this circle. This is where the wave starts. Phase just means where it starts. Does it start at 0? Does it start not at 0? So we might say that this is, let me do my quick math really quick. So this is 180. This would be 90. So does it start at 90, which is the top of the wave? Does it start at 270, which is the bottom of the wave? Does it start at 45, which is halfway between the 0 point and the top of the wave? It's in degrees because we're talking about a circle, so we've got 360 degrees. So what is the starting phase? Usually it's 0. I mean, if we're talking about a real normal sound, it usually starts at 0 because nothing's going on. And then something has to happen which then pushes air away. So it's always going to start at 0. Things don't usually start at 180. It's not, we don't have a lot of instruments that suck air out of the room, and then air moves to fill that, and then it sets up like some sort of oscillation. That's not a thing that happens. So usually these are going to start at 0. In fact, it's safe to assume, if you don't know the phase, you can assume 0. It's not always true, but you can assume 0. Okay, so let's take a look at amplitude here. So like I said, it's the height of the wave, and it's measured from the 0 point. So on this high amplitude wave here, it's going to be measured from this 0 crossing right here. The reason for that is that's 0, right? And so then from 0 it goes to positive numbers, and below is negative numbers. So we're going to have the same amplitude up and down. It's just going to be positive and negative. And this corresponds to how much pressure change there is from equilibrium. So we're going to have high pressure first, then of course it's going to be low pressure afterwards, but that's all from equilibrium. We don't want to look at the pressure change from high pressure to the lowest pressure, because that is this whole distance. We want to go from equilibrium. What's the ambient pressure in the room. So we have to go from the 0 point. If you measure distance from the peak or the zenith, which is this top of the wave here, to the nadir, which is down here at the bottom, that's going to be 2 times the amplitude. And if you measure to the center point, that is the amplitude. So what are the amplitudes of these top and bottom pictures? Well, it's pretty simple. I mean, my axes aren't labeled, so like, shame on me. But we can assume that we've got a line right here, so that's 1. We've got another line right here, and that's 2. So the amplitude of the top wave is 2, and we would assume that right here is -1 and -2 right here. So it's still 2. You can look down here, and if it's -2, the amplitude is 2. You're kind of taking the absolute value of whatever you're seeing in terms of amplitude. So it's going to be hitting 2, and it's going to be coming down here and hitting -2, so the amplitude is 2. And then this one right here, it only comes up to 1 or goes down to -1. And so the amplitude of this one is 1. Notice that these are both the same frequency. So these are the same, these would sound like the same pitch note. They just change in amplitude. Amplitude, of course, is loudness. So what these sound like is, the top one is going to sound like, and then the lower one is, like that. Same note. I hope I had the same note there. It's possible I didn't. They should be the same note. Same note, but different loudnesses. That's amplitude. Okay, what about frequency? Well, frequency is pitch, right? That's what we're interpreting as pitch. So low to high, what you're seeing here is going to go ooh, like that. That's a change in pitch. I think I also got louder. So it's actually like ooh, ooh. It's hard not to get louder when you get higher. But we'll talk about that when we get to speech perception. Okay, so frequency is related to the period, right? So the period for the low frequency wave is going to be from here to here. Period of the high frequency wave is going to be from here to here. So the period is obviously longer for the low frequency wave and shorter for the high frequency wave. So these are like inversely related, right? The longer the time between these two, the higher the frequency. We talked about that already, though. So frequency, how many oscillations you have in a given time interval, which again is usually 1 second. Hertz is how many cycles per second. So a high frequency tone here has more cycles per second than a low frequency tone. And again, there's an inverse relationship between frequency and time, or frequency and period, whichever way you want to say it. And so you just take the inverse of those, right? So if you know the period, you put 1 over period, that's your frequency. If you know the frequency, you put 1 over frequency, and that's your period. So there you go. So let's take a look at these two frequencies, and how would you figure out what these frequencies are? So let's say that each of these bars is 1 second. Oh, how did this get off? Shoot. When I put this into my slideshow, it was, the peak of each one was on a bar. Sorry about that. So let's assume that they are. Usually, I'm not ever going to ask you to assume that these frequencies are right on, because that can lead to problems. For this one case, let's assume that they're right on. So if this is right here, 1 second. Here's 1 second. A box of 1 second. How many cycles, how many complete cycles do we have there? Well, we'll start at the peak, 1.5. Interesting. So if we go to 2 seconds, what you should see is that we have 1, 2, 3. So we have 3 cycles per 2 seconds, or 1.5 cycles per 1 second. For our low frequency, which again is definitely shifted, which it shouldn't be, it should be one cycle per second. So we should have a line right here, and then we should go like this, and we should have 1 cycle per second. So 1 cycle per second, we don't need a calculator for that, because if you put 1 over 1, it's 1. So your frequency is 1 hertz, 1 cycle per second. And for our other one, you don't need a calculator for that either, actually, because we know how many cycles per second it is. So it's 1.5 hertz, 1.5 hertz. So it's a slightly higher frequency than the low frequency, and that's how you would compute that. Again, sorry for these being slightly off. In all of our other demonstrations, I want to make sure that they're precise, because you're going to have to actually physically calculate from one area of your wave to the next, and if you're slightly off, it can ruin your calculations. Okay, so let's talk about phase. This is where your cycle begins. So at your time period of 0. So right here at this line that comes down, this is where we're going to say our time period of 0 is. Sometimes this is when the sound starts, or sometimes this is just when you decide to start measuring. And so that's when you can end up with a phase difference being weird, is if you start measuring in the middle of a word or something, you might have your phase be off. But if you start measuring from the start of the sound, your phase is usually going to be 0. So when the phase isn't 0, it's going to look like your wave has been shifted one way or the other. So what you've got here is the dotted line is the actual wave. This is our starting at 0, right? Because we can see that right here at t equals 0, this is where phase is at 0, because it's going to start moving up from the 0 point. And that's phase at 0. That's good. Now, the yellow line has been shifted slightly to the left, right? In fact, it's been shifted 90 degrees to the left. So it, at t equals 0, starts at the top, at the peak of the wave. And so this is a little strange. This isn't what we usually see. And so phase is not 0. In fact, phase in this case is going to be 90. It's 90 degrees off. So it's kind of like you're trimming off the first 90 degrees, and it's shifting over. And so then we say that you're starting at 90 degrees. Because you still go through 180, which is right here. You still go through 270, which is the nadir of the wave down here. And then you go back to 0, or 360, right? Same thing. So here's another thing. This is where more people are going to die. Too much math. This is our formula again. This is just our formula for finding k of t. This phrase right here, 2 pi f, can be written as omega, lowercase omega. And so then we just say that the wave is shifted by phi over omega seconds. What the heck does that mean? Well, remember I said that we can say that the wave has been shifted by 90 degrees. And that's true. It doesn't matter what frequency you're at. If you shift from here to here, which is what this little yellow line is, so we've taken off 90 degrees, it's 90 degrees. Whatever frequency it is, doesn't matter. If you go to the peak if you start at the peak, it's shifted by 90 degrees. But that doesn't tell you how many seconds have been trimmed off of the actual sound file, right? Because if every frequency starting at peak is 90 degrees out of phase, then that tells us nothing about time. It only tells us about phase. So what you want to do is you have to divide phase by your formula for period. And so that's where the omega comes in here, 2 pi frequency. So it's figuring out where on the circle you are for the frequency that you have. And so then if you divide phi, your phase, by that omega number, which is frequency dependent, then you actually get how many seconds you're shifted in time. I'm not going to make you calculate that, so it's okay if that is kind of like a nebulous term in there. It's okay. If you have it, that's good. If you don't have it, go back maybe to look at some of the other ones and try to figure it out. It's important to know, but it's not something I'm going to test you on. So just be aware of that. You might need to know what phase is. You need to know what phase of 0 is. You might need to know what phase of 90 is. But I'm not going to make you calculate phi over omega. Okay. So how do we go from a wave to a spectrum? Well, kind of what we're doing is we're flattening the wave, basically. So the waveform, which is x of t, right? That's just the formula that we've been looking at is the formula for the waveform. So it plots the x of t against time. It plots displacement against time, phase or amplitude. Sorry, not phase or amplitude. Phase and amplitude and frequency are things that we're seeing all at once. It's really good for looking at sound kind of like holistically, like this is what we're hearing at our ear. This is what we're hearing at the microphone. In a way, this is what's coming out of our vocal tract or instrument, whatever we're playing. A spectrum, however, shows amplitude plotted against frequency. So it doesn't show you what it looks like over time. It shows you, boom, here is a line, this is your frequency. And so you can see that right here. So here's your typical waveform right here. This is what we've been looking at. This is x of t, typical waveform, anything like that. And so what it's doing is it's collapsing this. It's figuring out what the frequency is here, what the frequency is here, what the frequency is here. And it's going to give you the frequencies. How do we get this? We're going to talk about that on the next slide, I believe. Well, actually, it's a couple slides away, but here's our raw sound file. So here's an instrument playing a chord. It's periodic. You can see that it repeats itself. You can see that here's the nadir of the wave, and you can see that it traces this pattern. And then right here at the nadir, it starts over again. So we know that it's periodic. That's great. We're not totally sure. It kind of looks like maybe the phase is not starting in time right here, but that's okay. So here's our raw signal. And then what this Fourier transform is going to do, it's what the math is called to like pull all the different frequencies out. It's called Fourier transform. So it's going to pull all the different components out of this. It's going to look at, oh, there's a really high frequency tone, there's two middle, and then there's one really low frequency tone. And so it pulls all these out. Here's the frequencies. And then what it does is it collapses over time. You can see how this kind of looks like it's shifting like this, like towards you. So it's shifting, and then what you're getting is just to look at, here are the frequency spectrum. This is the frequency spectrum. You're getting, this is one frequency, this is another one. These are all the frequencies that are there. And then this is how tall they are. So you can see how much power each frequency has, but not at any point in time. Time is not in this graph in a spectrum. If you're looking at a frequency spectrum, frequency amplitude spectrum, it's not there. You can also look at a frequency phase spectrum if you wanted. It would just show you like where different frequencies start in, you know, what phase they're in at which portion of the sound wave. So it'll show you where they're beginning, like here's phase, this is in phase, this is 90 degrees out of phase from this one below, this is 180 degrees out of phase from this one. It's not one that we typically use very often. Usually we're looking at the frequency amplitude spectrum because we want to know what frequencies are present and how strong are they. That's what we want to know. And so that kind of answers my next point here is like, what's best? Well, it depends on what you want to see. I mean, if you want to look at the waveform to see a time representation, that's fine. And sometimes we do want to do that. We want to see where the sound starts. You'll be able to see it pick up. We'll want to see where is noise. You can really easily visualize noise because it'll go from kind of like a more periodic thing to a scratchy, noisy looking thing. So we can see where noise is and cut that out. But if you want to know about the frequency, like say we want to know what is my fundamental frequency or what are my formats of speech, which is what we're going to be doing in this class, well, then we want to look at a spectrum. We want to know what the frequencies are. Okay, that's all I have on that slide. Great. This is just another representation of a frequency spectrum. So this is kind of what you'd see in Prot. This bump right here is showing that there's energy at this frequency. This bump right here is showing there's energy here, more energy. Then this frequency here, there's a little bit less. And over here, well, here, a lot less. And then here, another peak, but less again. So this is your typical frequency spectrum from Prot. This is what they'll look like. And what you'll be curious about is like, where are the peaks of all of these bumps? Because that's telling us that there's a lot of amplitude at that peak. And this is how you tell, like, is something harmonic? Harmonic meaning all of the different frequency partials are aligned. We can also look for where the formats. Formats are going to be really high peaks of energy. So if this was a voice, you might see this right here. This is the fundamental frequency, which is the lowest harmonic peak. And then you might think that this is the first format, which is a harmonic peak that is amplified. So that's what we kind of use these for. Okay. So the time domain, which again is just your typical waveform, right? You're going to look at pressure or displacement or voltage as a function of time. You're looking at change over time, right? Some sort of fluctuation in time. Again, this is how the signal reaches our ears, how the signal reaches a microphone. Frequency domain is looking at amplitude and frequency. So time is not something that exists in this graph at all. What we're looking at is frequencies and how powerful those frequencies are. And this could be more akin to how we actually experience sound neurally or perceptually. How do we actually experience sound? Because we hear a tone, ooh, and it does unfold over time, but we do pull out just those particular frequencies. This is kind of oversimplifying it because, as we're going to talk about later, there's a lot of other things we do that kind of compresses all of the sound information into a perception. But anyway, that's for later. So it's important to also know that these are complementary and equivalent representations. You can go from one to the other if you have the right information. Like we're deriving the frequency spectrum from the waveform. We're going from that one to the other. And we can go from one back into the other if we are pulling discrete time points from our frequency spectrum. So we can go from our frequency spectrum back in if we say, like, this is 1 second. These are the frequencies that are present, so we can put that in for once. This is the second, and these are the frequencies that are present. Here's the third second, and here we go. And then we can reconstruct the waveform in time. So they're complementary. They're not at all the same, but they are equivalent. Like, we can move back and forth from one to the other. And then, like I said, the Fourier transform is what allows us to go from one to the other. So if we have a waveform coming in from, like, my microphone, I'd take this signal, I'd run a Fourier transform, and I'd see what frequencies are present in my voice, and probably on my computer it's making noise. There's probably some sort of noise that I can pull out from my lamp, all these different things. Oh, and that's the end. So we'll talk more about frequency through the rest of this module. And then I'm going to have a really short activity with Prot and Audacity to teach you how to play around with Fourier transform and what sine waves look like and things like that. Okay, I'll see you soon.